The last section in this book is about the natural log. And as we're looking at the natural log, we're going to need to know something about that number e, which we used in the PERT equation. So if you recall this equation right here, we had Euler discovered the number e. That was the value of $1 after 1 year of being invested at 100% interest compounded continuously. So if that interest is compounding continuously for a year and I invest $1, you'd have actually about $2.71 at the end of the year instead of just $2 if it were not compounded continuously. Pi, e, the square root of 2, all these numbers are irrational numbers, which means they can't be expressed as the ratio of two integers, and it does not repeat. So e is about 2.71828, but it'll go on forever without repeating. Goals today then, we're going to look at how can we evaluate natural logs and solve equations using the natural logarithm. So what's a common log? Well, a common log was anything with a base of 10. So if I didn't see a base written, that would be a common log. It was implied that the base was 10. Well, today we're going to look at what's called the natural log. E often appears as a base in math, just like with that PERT formula, and also science equations often involve a base of E, and is especially useful in calculus. So the natural logarithm is a logarithm with a base of E. So we've actually dedicated a special notation to a logarithm with a base of E, and that's this notation right down here. So if I write log base E of x, this would be the same as saying, okay, e to what power is x? Instead of writing log base E of x, I could, instead of writing this, just write ln of x, which is read the natural log of x, and this is implied that the base is e. So just like with a common log, if I didn't see anything written, I'd say the base is 10. If I see that ln, this is the natural log, it's implied that the base is e. So this means the same thing as log base E of x. It means e to what power is x. And here's some jewelry for your friends or loved ones if you're interested. So now let's evaluate natural logs. Well, if I see that ln, this means it's just a logarithm with a base of e. So all of these are natural logs, the base is e. This first example would be saying, well, e to what power is 1? And remember, e is just a number, about 2.71828. So 2.718 to what power equals 1? Well, anything to the 0 power would be 1. So if I were evaluating this log, the ln of 1 should equal 0. Second one, ln of e. Well, this means e to what power is e? So if there's no base written, but I see that natural log, my base is e. E to what power is e? Well, that would just be 1. E to the first power would give you out e. Last example, your base, again, if it's not written and I see that natural log, it's implied the base is e. So e to what power equals 1 over e to the third power? Well, e to the third power is the same as e to the, or 1 over e to the third power is the same as e to the negative third power. So this answer would be negative 3. E to the negative third power would give me 1 over e cubed. Now your calculator can evaluate natural logs. So if you find the log button, the natural log button is right underneath the log button. So we could check our answers. The natural log of 1 is 0, just like we found. The natural log of e is 1. The natural log of 1 divided by e cubed is negative 3. So we can check all of those answers on our calculator. So now let's tie this back into the section on inverses. If I want to find the inverse of the equation y equals the natural log of x, well, to find the inverse, I would just switch x and y. And the inverse of a logarithmic equation should be an exponential equation. So at this point, if I want to free up that y term and rewrite this as y equals something, I would write this as an exponential function. My base is e, so this is like saying e to the x power equals y. So y equals e to the x is actually the inverse of y equals ln of x. Now we had 3 log properties, and a natural log is just a logarithm with a base of e. So all these 3 properties that we've studied earlier on in the chapter also apply to the natural log. So a couple examples here. Write each expression as a single logarithm. So let's see where you're at with your knowledge of these log properties. Pause the video, try to do both of these examples, and then let's compare our end results. So applying the log properties, first I saw that 2 out front, I brought that up to the exponent on the argument. Then if I'm subtracting exponents, remember a log is an exponent, that would originally occur if you were dividing terms that had the same base. So eventually I can combine these into one log by dividing that 15 squared divided by 75, and 225 divided by 75 is 3. Now note that I could go to my calculator to check the answer. So the ln of 3 should be equivalent to 2 times the ln of 15 minus the ln of 75. So if you want to check that out, we got what? ln of 3. That should equal the original 2 times ln of 15 minus ln of 75. And sure enough, both of these equal about 1.10. So that's a good check that these expressions, the original and the ending expression, are actually equivalent. Second one, same thing. I could bring that 3 up as the exponent on your argument. 2 to the x times 2 to the x times 2 to the x would give you 8x cubed. And then if I were adding exponents, that would occur if I were originally multiplying terms with the same base. So combine this into 1 by multiplying, and your final answer, ln of the quantity 8x to the 4th, should be equivalent to your original expression. Now 2 last examples. Let's look at solving a couple equations. The first one, I want to free up x in the exponent and the base is e. So if x is in the exponent, I'd work by getting rid of everything that's not attached to that x term. So let's subtract 2. Let's divide by 4. So e to the 2x would equal 14 divided by 4. Or that would be 3.5. So e to the 2x should equal 3.5. Now at this point, if I want to free up x from the exponent, I could take the log of each side, or I could take the natural log of each side. It doesn't really matter. I'm actually going to take the natural log of each side. So I see x is in the exponent. Free that up by taking the natural log of each side. Then that allows me to bring the exponent out front. That's the whole reason I'd be taking the log or natural log of each side. So now I have that 2x's out front times the ln of e equals the ln of 3.5. Well, the convenient thing here about taking the natural log is this is saying your base is e. So this is like saying e to what power is e? Well, that would just be 1. So the natural log of e is just 1 because e to the first power is e. So now I actually just have 2x times 1, or just 2x, equals the natural log of 3.5. And the last step is I would just have to divide by 2. So if I take the natural log of 3.5 divided by 2, natural log of 3.5 divided by 2, I should get my answer. X is about equal to 6.26. So in the end, X is about equal to 0.626. Natural log of 3.5 divided by 2. Now, I could do this using logs. So let me show you what that would look like real quickly. So here we go. Instead of using the natural log, at this point, if you wanted to take the common log of each side, because your calculator will do the common log as well as the natural log, feel free to do so. You take the log of each side, bring that 2x out front. Now, before, I had, ln of e was just 1. Here I have the log of e, which means 10 to what power is e? Well, okay, I don't know that off the top of my head. So divide each side by the log of e, divide by 2, and eventually I'd get here. If you type this into your calculator, you should get out the same answer. So if instead I used common logs, I'd have the log of 3.5, all of that divided by the quantity 2 times log of e, common log. And sure enough, I get out the same answer. Using the natural log just maybe cleans up the equation a little bit more since your base is e, but the common log certainly produces the same answer. Last example, pause the video and see what you can come up with for this equation. So when I see ln, that's just a logarithm with a base of e. I can still use all those log properties, so I combine this expression, or this equation, the left side, ln of 2x plus ln of 3, that expression I could combine into one natural log by multiplying the arguments. So I have ln of 6x equals 2. Now what do I do at this point? Well, if I see that ln, that means natural log. It's implied that my base is e. So this really means e to the logarithm is an exponent, so the exponent is 2, and that should equal 6x. So if I want to solve for x, last step is I would just need to take e squared divided by 6. Now remember, x is the variable in this problem, that's what I want to solve for. E is just a number. So at this point I'd go to my calculator, and I could just take e squared, so e squared divided by 6, and that should give me my approximate answer. So x is approximately equal to 1.23. And again, if I can use my calculator, I'd encourage you to go back, plug this into your original equation, take the natural log of 2 times about 1.23 plus the natural log of 3, and you should get out 2. This video is dedicated to my plant, Leonard.